The equation for the energy of a free relativistic particle is given by the solution of, which can be positive or negative. The problem of negative energy solutions is that a particle with E greater than mc squared could jump into a state with E smaller than mc squared by emitting a high energy photon with more than 2 mc squared. As a result, atoms will not be stable. To solve this problem, Dirac assumed that all the negative energy states are occupied. Many books persist in presenting this model despite the fact that physicists have abandoned it long time ago for various reasons. It is also pedagogically very confusing. Indeed, you will inevitably remember only a hopefully large fraction of this course, and we don't want you to keep in mind the wrong picture that the vacuum is full of particles. The problem of negative energy solutions finds its solution in quantum field theory, the theory which merges quantum physics and special relativity. In quantum field theory, the energy of a free particle is always positive. However, if the particle carries a charge q, then quantum field theory also predicts that a particle with the same mass m but an opposite charge minus q should exist. Such a particle is called an antiparticle. Like particles, free particles have a positive energy. Antiparticles of positive energy offer a more realistic interpretation than particles of negative energy. The antiparticle of the electron is called a positron, noted E+. This new antiparticle was predicted by Dirac, but few people believed it, before it was observed experimentally in 1933. This figure shows the track of a positron in a cloud chamber. The thick lead plate in the middle slows down the particle, so it comes from the bottom toward the top. The curvature is due to a magnetic field pointing toward the page or the screen. The associated force is so the particle must have a positive charge. The upper track is too long to be associated to a proton. Indeed, the momentum of the particle can be deduced from the curvature. If it was a proton, with this momentum, the range, length of the track, would be much smaller. The positron was the first antiparticle to be discovered. We now know that every particle has an associated antiparticle, antiproton, antineutron. Note that the photon, however, is its own antiparticle. Antiparticles are usually noted with the bar. The antiparticles of U is noted U bar.